Okay, so hi everyone, welcome to Inspiration Exchange. This is our 44th session, and it's a very exciting one on learning system dynamics without equations. Before jumping into today's session, we just wanted to advertise the upcoming summer school in September. So this is the fifth iteration of the Cambridge Center for AI in Medicine summer school on AI and machine learning for healthcare. It covers a variety of topics. We've had almost 200 participants over the last 3 years, and I believe this is the fourth iteration. So it's a very exciting set of topics, and you can go have a look on the website for all of our different speakers. And we've opened early bird registration, so please take a look on the website. And then just highlighting our upcoming session in April before diving in, which will really cover AI agents, and that'll be on the 3rd of April, the next month. And for today's session, we're really excited to be joined by Dr. Rich Caruana, who's a senior principal researcher at Microsoft Research. We've got a very different session today, different from the conventional session where we're very privileged to have Dr. Caruana give us the seed presentation today around glassbox models. We'll then have the second part, which Krzysztof will talk about on learning systems dynamics without equations. And Krzysztof is a PhD, finally a PhD student in the lab. And thereafter, after Krzysztof, we'll jump into our normal panel discussion where we'll unpack some of the ideas covered in the first two parts.
Okay, cool. Hey, so we're going to talk about Glassbox learning and some of the surprising ways in which this is working very well now. Before I start, though, I've got to thank a bunch of people. In red, these are all graduate students who have interned with us. Green are developers at Microsoft. We have a bunch of doctors because you'll see a lot of my examples are healthcare. And then some other researchers from universities and other researchers from Microsoft. And of course, the work I'm going to present is work that all of these people have done over the last 10 to 12 years. Um, let's briefly start with a history of machine learning, right? You know, perceptrons, linear perceptrons in the 50s, k-nearest neighbor in the 60s, decision trees were invented in the 70s. The neural nets came back in the 80s, this time with a hidden layer. Then we started seeing principled methods like Bayes nets and support vector machines in the 90s. Around 2000 is when things like boosted trees, random forests started taking off, ensembles of trees, but SVMs were still around 2000. Then, of course, deep neural nets happened around 2010, and very exciting. Interestingly, though, if you're working with tabular data, it turns out that around 2010 to the present, gradient boosted trees and random forests are still sort of the best methods for tabular data. And then now 2020, we're seeing these large language models, and they're absolutely amazing on text. Deep neural nets are still very good on images. And now these large language models are even starting to be good on tabular data. So there's a really interesting question of, what is going to be the most promising method for machine learning for tabular data going forward? And it's been estimated that about half of the world's learning problems are tabular in nature. So this is an important question. Before I do that, though, let's just do a brief review of neural net history. First coming of neural nets, of course, was perceptrons in the 50s. The second coming was neural nets in the 90s with a hidden layer, now nonlinear. Then deep neural nets around 2010. And then the forthcoming of neural nets is these large language models and transformer models. And then, of course, as of last year, we have a Nobel Prize in neural nets, which is really, really exciting to see that. But the question remains, are neural nets like going to take over everything? Are they going to be king of the hill for tabular data also? Or are we going to see something else? And we think there is a chance that going forward, we're going to see large language models and transformers doing everything that has to do with text and images and possibly with planning and even with proofs in math. But we may see glassbox machine learning, what we'll talk about today, sort of be king of the hill for the next, let's say, decade or so on tabular data. And you might think, well, that doesn't make any sense because everybody knows there's a trade-off between accuracy and intelligibility. If you want high accuracy, you got to use black box methods like deep neural nets or transformers or random forests. And if you want intelligibility with glass box methods, you're going to have to accept a loss in accuracy. I'm happy to say that this is no longer true for tabular data. This was true 10, 15 years ago, but it is not true anymore. In particular, we now have a number of methods, generalized additive models, explainable boosting machines, neural additive models, the Rashomon set. We have a number of methods now which are competing in accuracy with all of the black box methods, but they provide intelligibility, and that's great. So that's what we're going to talk about today. Let me just give you some evidence for that. Here's 10 classification data sets. All of these numbers are AUCs on a test set. And here we have EBMs in the first column. These are explainable boosting machines. These are glass box models. And their average AUC on test data is 0.866. On the right, we've got glass box models, full complexity models that have been optimized to be highly accurate. And you'll notice the best of these on these 10 classification data sets is also 0.866. That is, we have essentially a tie in accuracy here between glass box and black box learning. And this is maybe some work you want to take with a grain of salt because I'm a co-author here. But then here's some work by Cynthia Rudin, another person who's well known for glass box learning. And they observe in their paper that, first of all, the best glass box model seems to be the model we're going to talk about today, these explainable boosting machines. And they also observe that the best interpretable models, the best glass box models, seem to perform about as well as the best black box models. And in their experiments, this was also XGBoost. So anyway, this is independent confirmation of this result that glass box and black box methods are comparable accuracy now on tabular data. So let me just briefly give you a history of glass box machine learning. So there was linear logistic regression. That's been around for a century. Then decision trees, if they're simple, it turns out trees are interpretable. If they're large, they're not interpretable anymore. But simple decision trees are definitely glass box. Then generalized additive models were invented at Stanford in the late 80s. So this is the first serious modern learning method that I would say has a chance of being accurate and is very interpretable. In healthcare, by the way, they use lots of things like nomograms and additive tables. So these are a simplification, if you will, of generalized additive models. Then what we'll talk mainly about today are these explainable boosting machines, sometimes called generalized additive models with pairwise interactions. But there are optimal trees from Cynthia Rudin's group. We'll talk briefly about neural additive models. It's another way of doing generalized additive models using neural nets. And then there's now starting to be methods that use transformers to train these generalized additive models called GAMformer, but we won't talk about that. That's very, very recent. In fact, that's not published yet, although it might be available in arXiv. Okay, let me tell you what these things are. The simplest additive model is linear regression, straight line for every feature. And if you wanted to do classification, you pass it through a sigmoid to get the predictions to be on the interval 0, 1. So they're well-formed probabilities. Very interpretable. The models are very simple. In fact, we don't usually draw graphs. We just have a table of slopes. Not very accurate on complex data, and that's because it can't model nonlinearities. And sometimes this thing, even gets the sign of coefficients wrong. So you really have to be careful when using something as simple as a linear model on very complex data because it can't fit the data well. And because of that, it doesn't get things right. Now, at the other extreme, we've got black box machine learning. This is neural nets, deep neural nets, boosted trees, random forests, things like that. Not very interpretable. That's why we call it black box, but it can be very accurate because it can model nonlinearities. So that's great. One thing you'll find is these things tend to be a little twitchy. They're prone to overfitting. Because of that, they're more likely if you open them up with, say, SHAP and try to understand what's going on inside these models, you'll find some of what they learn is sort of spurious effects that are not really well supported by the data. In the middle, we have what you might call the Goldilocks models, the models that are just the right complexity. They're more interpretable than linear logistic regression. This blue line is an example of one. So instead of just being a coarse straight line, you can actually see detail, like the response is flat here and low, rises rapidly, then it's flat above, and it even is rising a little bit on the left. And if you think about it, a straight line can't do this kind of detail. But this nonlinearity is enough that if you do it really well, these models can be very accurate as the black box methods. And that's because they can model nonlinearities. They can even be multimodal if necessary. And then what's important is because of the restriction of these model classes, they're more likely to show real statistical effects that are in your data. We didn't invent these. They were invented by Trevor Hastie and Rob Tibshirani, very famous statisticians at Stanford in the late 80s. And what our contribution is going to be, these were invented before machine learning, before the internet, before large data sets, before big computer horsepower. What we're going to do is we're going to start using modern machine learning techniques to train these generalized additive models that they invented. And that's where EBMs are going to come from, explainable boosting machines. So we're going to use boosting under the hood to train these models. And we're going to use a lot of computer horsepower. We're going to do some modern tricks. And we're going to get these things performing comparably to these black box methods. But we're going to do that without throwing out their interpretability, their glass boxness. So let me mathematically just briefly show you what that is. A linear model, of course, is an intercept, slope times a feature, slope times a feature. Full complexity model, well, it depends on which one you're using. Don't worry about it. It's just some arbitrarily complex function of all the features. In the middle is a generalized additive model. It's a function of the first feature plus a function of the second feature. So we have a function for every feature and use addition to combine these. So now this is a very restricted model. The functions can be complex, nonlinear, multimodal, but we're not doing any complex combinations of features. If we want to do that, we can. So here's a sum of functions of individual features that are these main effects that are up here on this line. But here's a sum of functions of pairs of features. So now this could do pairwise interactions. And if we want, we can do sums of functions of triples of features and do three-way interactions. We'll actually restrict ourselves to main effects and a small number of the most important pairwise interactions. And we have a heuristic method that automatically finds these important pairwise interactions for us. Let me give you an example now. We'll spend about 5 minutes on this. This is pneumonia mortality. So you all have pneumonia, you've been diagnosed, and our goal is just to figure out which of you are high enough risk of dying from your pneumonia that you should be in the hospital or the ICU, and which of you are low enough risk, as most patients are, that they should be treated as outpatients. We've got 46 features, and remember this model is a function of a feature plus a function of a feature, so we're going to have 46 functions. We'll throw in 10 pairwise interactions. So we're actually going to have 56 functions and an intercept. From a high level, this is what this looks like. So here's a function of pneumonia mortality risk as a function of age, plus a function of risk as a function of your asthma, all the way down to a function of risk as a function of your blood urea nitrogen. Remember, there's 56 of these in the model. And the way you use it is you look up the patient's age on the x-axis, read off a contribution to risk on the vertical scale, and then you write down a number. So just like a slope times a feature would give us a number, here you're doing lookup in these graphs, and that gives you a number. And then we add all those numbers together. And that gives us a score, and the probability of mortality is 1 over 1 plus e to the minus score. This is standard logistic regression. In fact, if this were a standard linear logistic regression model, we would just have a straight line up here in the exponent, and all of learning would be trying to learn the straight line that works best with this formula to predict probabilities. But instead, we have these nonlinear graphs up here. So what we're doing is we're learning a score, which is a sum of numbers that are read off of these graphs. So this model is just significantly more complex than linear models, but because these are graphs, they can be interpreted. Okay, let's jump in. This is what the model has learned about the patient's risk from pneumonia as a function of the patient's age. So I'm going to interpret this graph for you. Down is low risk, up is high risk, and these are logits. Okay, so if this was a neural net with a sigmoid output, these would be the hidden activation for an age hidden unit sitting at the output layer of the neural net just before the final output. So these are logits, so they're on a log scale. So a small difference makes a big difference here in probability. And these graphs are learned all together. Okay, so this is not marginalization. This is learning risk as a function of age. At the same time, the model is learning risk as a function of blood pressure, risk as a function of gender, and things like that. Okay, so let me interpret this model. Well, lowest risk is all the young patients. It's good to be young, and everybody under 50 seems to be sort of equally low risk. The model statistically doesn't see any reason to distinguish between people in their 20s, 30s, and 40s, even though it could. Then risk goes up slowly as you go through your 50s into your 60s. Surprising rise in risk right around 67, 68, 69. We see this in data in the US, but not in other countries necessarily. This is a retirement effect that we see in the US. In the US, retirement often changes your healthcare insurance and your provider, and maybe your urgency to get to care because you're not going to work every day, and maybe where you live. So a lot of things change when you retire, and we see that at least for pneumonia risk, it causes a rise in risk. Then risk goes up pretty rapidly as you're going through your 70s into your 80s. That makes sense. You're becoming elderly. Surprising step function rise in risk right at 85. That's surprising. Surprising flatness of risk in the 80s and 90s. And then a really surprising drop in risk right at 100, 101. This rise in risk at 85, there's nothing in healthcare or insurance policy in the US that says you should treat patients who are 86 different than patients who are 84. We're pretty sure what's happening is the typical life expectancy in this data set is about 79 or 80. So patients over 85 are definitely on the elderly side of being elderly. And we think they're getting less aggressive care because they're considered very elderly. As in, grandpa's 87, grandpa has a number of illnesses associated with being this old. Now grandpa's got pneumonia because of these other illnesses. The first two rounds of antibiotics haven't helped. Maybe we're not helping grandpa. Maybe we're not doing him a favor by continuing to fight. So we think there's a tendency to be a little less aggressive in care for patients above 85, and we see a rise in risk because of that. The exact opposite we think is happening at 100. If a patient has made it to being 100, 101, maybe their 101st birthday is 2 months from now, the doctors, if it's a treatable illness like pneumonia, often just will not give up on the patient. It's like, we're going to get you to that 101st or 102nd birthday. If you need 3 or 4 rounds of antibiotics, of the best antibiotics we got, we're going to do it. We're going for the record. And that's because you've made it to being 100. You've made it to being a centenarian, which in this data set is really kind of remarkable since this is a 30-year-old data set. So that's really amazing what the model has learned, all this sort of nuanced detail. Everybody under 50 is equally low risk. 50, 60 is not too bad. There's a retirement effect. Getting old, of course, puts you at higher risk. 85 is a surprising jump in risk because you become ultra elderly. But if you make it to 100, because you've made it to 100, doctors won't give up on you. So that's really interesting, nuanced story. And remember, there's 56 graphs like this. We don't have time to go through all of them. They all tell interesting stories. Interesting thing is, this is the most accurate model anyone's ever been able to train in the data. So we haven't lost any accuracy in getting this sort of intelligibility. Another interesting feature is no one actually believes that medically a 105-year-old is lower risk than a 95-year-old, even though the model has learned that. We believe because the patients who are 105 are getting more aggressive care. So we can edit this model. The model really is these graphs, which means if we change a graph, we will change the model. And we can make risk, for example, be monotone increasing above age 85. Let me show you some surprising things that this interpretable model has learned about pneumonia. First of all, it's learned that having asthma is good for you. These are the asthmatics, and their risk is lower. It's learned that having a history of chest pain, and I'm not showing it, but a history of heart disease is also good for you. Like asthma, heart disease is good for you if you've got pneumonia. And it's learned that having stridor, which is a terrible kind of wheezing, which indicates you have obstructed airways, advanced pneumonia, it's also learned that that's good for you. Now, none of this makes sense. Like if you've got pneumonia, how can asthma or heart disease or advanced pneumonia, obstructed airway, how can those things be good for you? It turns out the asthmatics notice their onset of symptoms early. They try their inhaler or other meds. It doesn't work. It's not designed to treat pneumonia. They have a doctor who treats their asthma, so they know who to call. And the doctor says, oh, the inhaler didn't work. Get in here. They get an early appointment. And then the doctor recognizes, hopefully, that they've got pneumonia. And the doctor's thinking, well, you got a history of asthma. You're actually at high risk. And they get really high quality care and they get it quickly. And that's so valuable that the model has learned that having asthma is good for you because it causes you to get to care rapidly. Same thing for chest pain. So you might have had a heart attack a few years ago. You feel funny, your chest feels funny. You think you might be having another heart attack. If you're smart, you're in an ambulance right away, in the emergency room very quickly. Hopefully they recognize that you have pneumonia and then they treat you for that. Stryder, the same sort of thing. It turns
Hi,
out,
Rich. So I think you have
yes,
about approximately like 5 minutes,
okay,
around
great.
plus minus.
So it turns out that the Stryder patients, they have a symptom that you can't ignore. So they're going to respond to their symptom and get to care. Now, we can fix these models by flattening this and make it go away, just like we created monotonicity in the age graph. Or the doctor can say, no, high risk for the asthmatic, even higher risk for the heart disease patients, and highest risk for the obstructed airways. So we can make all of these changes. And we have a tool, a Photoshop for these generalized additive models called Game Changer. And notice that two of our co-authors are doctors who helped us develop this tool. This is Jay Wang's work. And this tool lets us take, say, this is risk as a function of age, very noisy graph. We don't believe that risk is actually going up and down like this. And we can do automatic post-processing to make this graph monotone. And these are the edits. And one of the ways we can do this is with like the pool adjacent violators algorithm. Or a person can go in and anytime they see a place that needs to be edited, they can go in and they can automatically edit these graphs. So they can do some amazing stuff to sort of fix defects that they find in the graphs. The most important take-home message here is that, it's not the case that a 105-year-old asthmatic with a history of heart disease who now has Stryder is low risk. Our model is predicted with high accuracy for predicting that. And that's because our test set looks just like our training set. But that's not the correct model given how we plan to use it. So accuracy and correctness are not the same thing. And you always want your model to be correct instead of accurate. If your model is correct, it will be accurate on future data, even though it might be a little less accurate on retrospective test data. That's very, very important. And ask me questions about that later if you're interested in that. You can get new discoveries from these models too. This is blood urea nitrogen. And I just want to show you that we get a flattening in risk at 50 and a peak in risk at 100. And then risk comes back down. And these are due to treatments, a pill that's being given at 50 and dialysis is being given here at 100. And then what's kind of a shame is the patients who are getting dialysis are the ones with blood urea nitrogen over 100. The patients under 100 probably aren't getting it. So we've actually got 100 patients with a blood urea nitrogen of 120 are lower risk than healthier patients who have a blood urea nitrogen of 90. And we can even estimate with this kind of model, we can do like spreadsheet what if kind of analysis and figure out that if we were to edit the model and move the dialysis threshold down to 85, that in the US, we'd save something like 2,500, 5,000 lives per year, and we would save more than 50,000 lives worldwide. And that's just by looking at one graph in one model trained on one data set and making one change to how we deliver care. So it's kind of remarkable what you can do. We see, by the way, these jumps in graphs all over the place. This is blood pressure. It's not the case that as your blood pressure continues to go up, your risk goes down. Then it goes up and goes down, goes up and comes down. This is all because you're hitting different treatment thresholds. And it's really cool that the model is peaking right here at 180 because that's the definition of hypertensive urgency, as opposed to 175. So it's really cool that the model has the sensitivity to learn these sorts of details. Let me give you an example. This is ICU mortality. This is a measure of how much oxygen is in the patient's blood. And the model has learned high risk if there's low oxygen, low risk if there's high oxygen. That makes sense. But there's a very surprising effect here. And this effect is just as low risk as the healthiest patients, but it's in a region of high risk. So, and it turns out missing values before we got the data were imputed with the mean. So we have a lot of very healthy patients who they didn't bother to measure this PF ratio test for. They're very healthy patients. They should be out here, but they've all been put here in the graph, and the model is doing everything it can to learn this. And we've tried other imputation methods. It turns out all of them are even more dangerous. So you might have thought that imputation, if you did smart imputation, would save you here, but that's not the case. So what happens is it moves the mass to the wrong places. It ends up making what our high-risk patients look like low risk, and you have to handle missing values in a completely different way. And glass box learning has just completely changed how we deal now with missing values. I'm going to skip over this neural additive model. So I just want to say, and this is joint work with some people at Google, at Microsoft, and with Jeff Hinton at Toronto, but we can train these same sorts of graphs using neural nets. And if you're interested in this, either I can come back and talk about it or ask me during the question session. So, but let me skip over this just for the sake of time. Another thing that's really cool about these models is because they're so simple, they tend to be pretty privacy preserving. And it turns out this is the privacy axis on the x-axis here, and this is accuracy on the vertical axis, AUC. And the red and orange are the differentially private version of these explainable boosting machines. And the green and blue are the best other methods in the literature. And you can see the accuracy stays high for the EBMs, but it drops for these other methods. So it's kind of nice that because these methods are simple and high accuracy, we can also get high accuracy with differential privacy. So that's great. And then I'm just going to wrap up by saying, surprisingly, if the model's interpretable to humans, it's also interpretable to LLMs. So for example, an LLM can understand this risk of pneumonia mortality as a function of age, and we can do queries, and it can answer things like, is risk rising monotonically with age? It can find surprises, like it can say, it's weird that negative albumin levels, which are physiologically impossible, are showing up on the graph. Or it's weird that with creatinine, there's a decrease in risk above 5, even though high creatinine is considered high risk. So we've done some work where we've compared real doctors to an LLM in a blind study, trying to find anomalies in data sets. And it turns out the LLM is not bad. And this is GPT-4. So this is actually old work. The new LLMs are even better. The LLMs are not as good as the doctors, and they're not as good as the most senior doctors, but they are already useful. And they did find one or two things that we were surprised by. Okay, let me just wrap up. Every data set you've ever worked with, tabular data set, has these sorts of problems. It's great that glass box learning is now ready for prime time, and there are a number of methods out there. You don't have to accept a loss of accuracy. You can now edit these models to correct mistakes. In some cases, you can guarantee privacy, and you can even use LLMs on these models to help you as an interface to the models for people who don't want to look at graphs, but also to help you find surprises. And the most important takeaway message, I think, of this work, now that we can see high accuracy of glass box models, is that we're learning that accuracy on retrospective test data is not the same as correctness, and you always want your model to be correct. So correctness is our goal. Okay, I just want to say thank you, and I'll stop.
Okay, so yeah, hi everyone. My name is Krzysztof, and today I would like to talk about work from our lab about learning dynamical systems. And in particular, I would like to present our recent work, No Equations Needed, Learning System Dynamics Without Relying on Clues from ODEs, authored by me and Michaela, that has been recently published, accepted for iClear 2025. So the focus of today's topic is data-driven learning of dynamical systems. And dynamical systems are really any kind of systems that evolve over time. And we can have, for instance, climate or weather, similar kinds of systems in ecology. We might have disease progressions, pharmacological systems, and also in finance, things like companies or stock data also evolve over time and can be considered as dynamical systems. But we don't really want to focus on all dynamical systems. We specifically want to focus on systems for high-state settings, such as healthcare. And in these kinds of settings, as Rich also mentioned, we don't really want to use these black box models. We want to use something that's more transparent, something that can be deemed safe, something that basically behaves as it is expected. So the question is, what kind of models for dynamical systems can we use? And we can turn our attention to probably the most famous models for dynamical systems, which are differential equations. They're even synonymous sometimes with the word dynamical system. In particular, ordinary differential equations, and I'm showing some examples here. So we have equations for tumor growth models. We have compartmental pharmacological models. We have SIR epidemiological models, or finally, Lotka-Volterra prey-predator model. So these equations have been designed by scientists through like a lot of manual effort. But the question is, can we actually learn them from data? And the answer is yes. And we have area of machine learning called symbolic regression, and in particular ODE discovery, that deals with discovering this closed form mathematical equations. And when I say closed form, I really mean a mathematical equation that consists of these numeric constants, variables, arithmetic operations, and some well-known functions like logarithm, trigonometric functions, exponentials, and so on. And actually, our lab has done a lot of work in this area. So I'm just highlighting here a few papers from our lab on that topic. But really, we can ask ourselves, why equations actually? Why do we want to use equations? What properties do equations have that black boxes do not? And in my view, I'd argue the most important thing is that we can analyze these equations to learn about system behavior. And this kind of analysis we can perform for a lot of closed form expressions, but we can't really do it for most black boxes in general. However, it seems that we're focusing a lot in ODE discovery on this closed form expression, on the actual equation. But what we really want is this understanding of system behavior. So we're focusing on something we call syntactic representation of a dynamical system, but we really want to understand its semantic representation. So let me maybe dive a little bit deeper into it. So every ODE can have these two kinds of representations: a syntactic representation, which is really its symbolic form, and its semantic representation, which describes the behavior of a dynamic system. It can be more about the shape of the trajectories, its properties, and how they change under different conditions. So to give a concrete example, we can consider a logistic growth model, and we can represent it as these simple equations with some initial condition. But we can also consider its semantic representation, or more precisely, the semantic representation of the underlying forecasting model, because every ODE has its own associated forecasting model where we can start with an initial condition and then solve the initial value problem and get the whole trajectory. So in that case, we can see for different initial conditions how the shape of the trajectory looks like. So if we have very low initial conditions, the trajectory is increasing. If we have higher values above a certain threshold, the trajectory would be exponentially decaying, for instance. And we can go even deeper into these properties. So we can analyze the maybe asymptotic property, how the trajectory behaves when time goes to infinity. We can maybe look at the inflection point and how it changes with different initial conditions, or maybe how this horizontal asymptote, or the midpoint, changes as well. So what I really want to say is that very often we in ODE discovery want to discover these closed form expressions, but they are really only a way to get this semantic representation at the end. And this is what we call two-step modeling. So this is a way of getting the semantic representation of a dynamical system using ODE discovery in two steps, where in the first step, we use ODE discovery algorithm to discover an equation, and then a human analyzes this equation to get this semantic representation, this understanding of the behavior of the system. And this kind of procedure has a few disadvantages. So first of all, the whole analysis may be very complex. It may be time consuming, may require mathematical analysis. Sometimes it may be intractable or impossible if the equation is too complex. Another thing is it's quite difficult to inject prior knowledge, because we often might have some prior knowledge about the phenomenon, but not necessarily about the functional form of the equation that best describes it. So it may be difficult to know whether there is a particular term, for instance, in the equation that we want to describe. It's also challenging to edit. So imagine you have an equation, but then you kind of verify it, you look at it, analyze, and then you see that something is wrong. The behavior is not what you want. Now going back to the equation, changing any of the coefficients, or whether to add the term or subtract the term, it's usually quite difficult to do in general. And similarly, providing feedback to the optimization algorithm is also quite difficult for the same reason. So what we really want to do and what we propose is this alternative to two-step modeling that we call direct semantic modeling. And that approach, we actually use the data set to directly fit the semantic representation of the dynamical system. And only later, this semantic representation determines the predictive model that we use for prediction, training, and so on. And the main difference between, and the main advantage of using this direct semantic modeling is that it's much easier to inject prior knowledge, because because our model describes the semantic representation, it's much easier to put this into the optimization process. Similarly, it's much easier to edit it because we can directly edit the semantic representation, because this is what our model is. And it's easier to provide feedback to the optimization algorithm. And the main difference between these two approaches is actually how the predictive model works. So in ODE discovery, the predictive model is basically, we take the initial value and then we solve this initial value problem, for instance, using Euler method to get the trajectory. Whereas in our setting, the predictive model consists of these two steps, where we take the initial value, then we use a semantic predictor to predict the semantic representation of a trajectory, which is what I said, like, it can be a shape of the trajectory, some kinds of properties, and so on. And then we use the trajectory predictor to actually match this representation to a trajectory. So this is the general framework. And now I would like to show a particular instantiation that we call semantic ODEs that fulfills this kind of criteria. And to do that, we first have to formalize what really is a semantic representation of a trajectory. And fortunately, not long ago, we published a papers called Towards Transparent Time Series Forecasting, when we provided a conceptual framework to describe a shape of a trajectory. And we describe it in the following way. So given a trajectory, we want to divide it into smaller intervals, where on each interval, the trajectory has a particular shape. So for instance, it is increasing or concave, or increasing and convex. So we have these different kinds of shapes, and we call them motifs. And then we can take a sequence of these motifs, and that we call a composition, and then describes the general shape of the trajectory. Moreover, we also have these transition points between the different motifs, which very usefully can be mapped to things like local minima, maxima, and inflection points, which are very often of great interest in modeling. So what we do in this work, we kind of borrow this conceptual framework. We extend it a little bit to make sure that we also have motifs describing unbounded trajectories, because in ODEs, we're also interested in a long-term behavior on a system, not just on some bounded domain. And we also add these additional motifs to differentiate between whether the trajectory approaches an asymptote or whether it does not, because that also seems to be very important while modeling dynamical systems. So to define the semantic representation of a trajectory, we have these two elements. One of them is the composition of a trajectory that I've just described. And then we have a set of different properties. And these properties include these transition points that I described earlier, but also some derivatives for some technical reasons. So we have derivatives at the beginning and some derivatives at the end of the trajectory. And also, very importantly, the properties of this final motif. So it might be, for instance, the horizontal asymptote, or how quickly it approaches a horizontal asymptote, to kind of describe this long-term behavior of the system. And then the semantic ODE method model works in the following way. So we take the initial condition, we use a semantic predictor to get the semantic representation of the trajectory, and then we use a separate model that we call a trajectory predictor that matches this semantic representation to a particular trajectory. And in this presentation, I'm not going to jump into the trajectory predictor. What's important to know, this part of the model is not really trained, it's fixed. And what it does, it searches a trajectory in a particular hypothesis space whose representation matches the one predicted by the semantic predictor. What I'm going to focus in this presentation is how the semantic predictor works. So how we define it is using two different smaller predictors, one called the composition map that predicts the composition, and the property map that predicts the properties of the trajectory. So a composition map, when you think about it, it's really a very simple classification algorithm. It takes a real value and then assigns a particular composition, so a particular class. So we decided to use a very simple classification algorithm that basically takes a real line and then divides it into subsegments and then maps each subsegment to a different composition. So this is an example of a composition map for the logistic growth model you saw before. And as you can see, we have different compositions for different ranges of the initial condition. The other part is the property map. And actually, this property map consists of a few property submaps. for different compositions. So previously you saw we actually have 3 different compositions. So we train a separate property map, submap for each of the compositions. As an example, you can see this is one of the property submaps for the first composition. And it really consists of this univariate function, because what we really want is to map an initial condition, some x0, to a real value corresponding to a particular property. So we have here property functions for the t coordinates of the transition points, the x coordinates of the transition points, the derivatives, and the properties of the final motif. So that, for instance, the horizontal asymptote or the time how quickly it approaches this asymptote. So this is basically the same thing that I've shown before. So now that we have this general description of the model, let me just show you in practice how that can be used and what really the advantages are. So to make it a little bit more concrete, we're going to consider a simple, very important problem, which is predicting, which is a dynamical system describing the drag concentration over time. So we can approach it from 2 different ways, and we're going to see like what are the advantages and disadvantages. So the traditional way would be to use something like ODE discovery. And the first thing where really semantic ODE shines is incorporating prior knowledge, or something we call semantic inductive biases. Because in ODE discovery, really what we can do is to put syntactic inductive biases. So this is prior knowledge about the form of the equation. So a very common assumption made is that the ODE is a linear combination of terms. So this is what methods like SINDI assume. Another kind of assumption is what kind of terms we can use. But as I said, it's usually quite difficult to know whether a particular term should be there. Should we include x times t? Should we include a logarithm? Like it's quite often it's not that clear. Another kind of assumptions would be how long the equation is. Should it be just 5 terms, 10 terms? Maybe we should discard coefficients below a certain threshold. What's really important is that all of these syntactic inductive biases are really about making sure that the equation is of a proper form to analyze it later. So it's not really about how the system behaves and like what your knowledge is about the phenomenon. It's really, let's make the equation simple enough so we can understand it, right? Whereas in our setting, we can have the semantic inductive biases about the shape of the trajectory. So in that case, we, for instance, can very well assume that if we have a drag concentration curve, if we're not giving any additional dose of the drag, then in the long term, it should decay to 0. So the final motif should be this decreasing convex motif approaching a horizontal asymptote. So in our composition library that we use for training, we can include only compositions where this is the last motif. And we end up with this 5 compositions that I highlighted here. This is also assuming that our composition is not too long. So we're also assuming that the trajectory is not likely to go up and down many times. So this is one of the examples where we can use prior knowledge and include it into our model. The other big advantage is actually comprehensibility. So we trained different versions of SINDI, which is this ODE discovery algorithm with different number of terms, and also our model on a synthetic pharmacological data set. And what we can see is that either we get a very simple, nice equation, but whose performance is not very good, or if we really want to get a better performance that's on par with our model, we have to get these very long expressions, which at this point it's very difficult to analyze, and also they're quite likely to overfit to the data. So if we look at the out-domain error, it's incredibly high. Whereas if we look at our model, it looks like it. So this is the whole model. We have on the right-hand side, we have a composition map that describes the shape of the trajectory. In this case, it learned that it has the same shape for all data points, which kind of makes sense. And this shape is basically a trajectory going up and then down, approaching a horizontal asymptote. And then on the right-hand side, we have these different property functions describing the coordinates of the transition points, the derivatives, and the properties of the final motif, which is the horizontal asymptote and how quickly it approaches it. And you can, for instance, read from it how the maximum of the trajectory depends on the initial condition. What's also important is that we can actually edit the model. So you can see here that this horizontal asymptote is not exactly right, because it should be zero. The model should work in a way that trajectory decays to zero as time goes to infinity. But because we work in the semantic space instead of syntactic space, we can very easily edit it. So we can edit our model and actually retrain the rest of the model while fixing this asymptote to be zero. And what happens is that we get another model where the performance for time outside of our training domain is comparable to our training domain, which is pretty interesting. And we also can improve extrapolation. So previously I've shown extrapolation in time domain. We can also do extrapolation for different inputs. So this model was trained for inputs between 0 and 1. And what we later did is we looked at every of these property functions and then fitted a linear regression to it, just a simple model, and then used this linear regression, this line basically, to extrapolate for inputs outside of the training. So for inputs between 1 and 1.5. And we ended up with a new model that basically has a very similar performance outside of the training domain as inside the training domain. And this performance is much better than any other ODE discovery algorithm we tested. So there's different versions of SINDI. And what's more important, it has this performance without seeing a single sample from this distribution. So I think it's pretty remarkable and shows how we can use our prior knowledge and understanding to improve the model. And finally, we gain flexibility. So discovery algorithms are pretty good if the model is, if the system is described by a closed form ODE, but we can also have ODEs more general, not necessarily closed form. We can have ODEs with multiple systems, but we only observe one of them, for instance. We can have delayed differential equations, integral differential equations. And in these cases, things like SINDI do not really work, but because we do not make any assumptions like this, we can have model that performs pretty well, and actually in many of these cases performs better than some black box models we tested. Okay, so that's pretty nice and good, but the model I presented is quite simple. So it only works where the input is really the initial condition, so one real value. And in reality, we would like to have it work for much more complex inputs, much more interesting problems. Like, for instance, we would like to take patient covariates, the dose of the drug, and predict the whole drug concentration curve. And this is an example of something we call a personalized dynamical system. And it's actually our current research, how we kind of extended this framework to more complex inputs. So this is still quite new, recent work. And the real challenge is actually to extend the semantic predictor from just taking one value as an input to taking a whole feature of values. So how do we do it? So we have this very simple classification model. What we need is a more complex classification model, but that is still interpretable. So we can turn to the most famous probably classification model, interpretable classification model in machine learning, which is a decision tree, right? So now we take this feature of values and we put it through a decision tree, and at the end we predict the composition, so the shape of the trajectory. And what can we do with the property functions? So this is no longer a univariate function. We have to find a different kinds of model. And fortunately, we have these models called generalized additive models. So we can now describe each of the property of the trajectories using a generalized additive models, which is very nice, clear, intuitive, and can also be edited, understood, and so on. So we really do not lose the transparency we gained in semantic ODEs when we go to these higher dimensions. We can still have quite interpretable and powerful models. And we actually tested it on a real data set, so on a real pharmacological data set where we needed to predict this drug concentration curves over time. And not only we got performance better than ODE discovery methods on par with black box models, but very importantly, we got performance better than the expertly designed population pharmacokinetic model. So I think it really shows that there is a lot of room for this kind of flexible but still transparent models, and they may have a real impact in real world. So kind of to conclude, the framework and the models we discussed allow for transparent and intuitive approach for modeling dynamical systems. They allow us to skip this complex analysis step and directly predict the system behavior so that we can quickly validate and adjust the model in real time. It also shifts the focus from the equations to the system's behavior, so it allows for more flexibility. We no longer have to make all these assumptions about the system. And finally, we hope it bridges the machine learning and human knowledge so that we can have scientific models that are not only powerful, but also usable and can be actually deployed in practice. So yeah, thank you very much. And I encourage everyone to take a look at our papers. And if you happen to be at iClear this year, then yeah, please say hello during the poster session. Thank you.
Awesome. Thanks so much for that, Krzysztof. And then everyone, so I guess in the essence of time, we might want to move on to, I guess we have many questions in the chat. So we've got questions for all of our speakers, but I'll start going through the list. And if anyone wants to just unmute themselves and ask the question, if not, I'll read it out. So the first is from Elena Sizikova. If you'd like to unmute yourself. And
Hi, my name is Lena Sizikova. I'm a research scientist in DE, and I found sort of both presentations extremely interesting. For Dr. Caruana's presentation, I had two questions. So the first was that basically if I think there was a slide with EBM model risk for pneumonia. So when you mean risk, does this risk like a model estimated risk, sort of like confidence in a deep learning kind of work, or is that like clinically meaningful risk, and whether it is easy to basically calibrate this risk with a factor that is clinically meaningful? That was my first question. And the second question was more broad and sort of what is the relationship of these models to like deep random forests or other kind of similar methods that are hybrid?
Right, let's see. So in the pneumonia case, what the model is trained to predict is a probability of mortality. And it is a well-calibrated model right out of the box. So usually we don't have to do any post hoc calibration to make it good. It generates good probabilities. And in addition to generate, probabilities, a risk score, basically, it also generates an error bar, a confidence interval around that risk score. So you have an idea of how confident it is. So it is kind of similar to any other very good machine learning method in that it can predict probabilities and it can give you confidences of those probabilities. And in this particular case, they're already well calibrated by design, which is good. In terms of similarity to other methods, we often find that black box methods learn a lot of qualitatively similar things in them. That is, sometimes you really want to use a black box method. It still makes sense to train a glass box model, look at the model, see what it's learned from the data, because it's telling you about what's in your sample of data. And then usually what happens is a lot of what's been learned by the glass box model is also in the black box model. You just can't see it so easily. SHAP sometimes makes it easy to find some of the effects. Sometimes it's not so easy because SHAP is an approximate view of what's going on inside a complex black box model. But basically, we find that all models that are very accurate on a data set, like 95% of what they're learning is pretty much the same thing with some differences. As I said, the black box models tend to be a little overfitty, a little twitchy, so they tend to learn some things that maybe aren't well supported by the data, including higher order interactions that aren't well supported by the data, whereas our model is restricted from doing that. But if anything, our model is a little too simple and the black box model is a little too complex, but they often learn very similar things. And by the way, that means that if you have a problem in your data set, like your model is learning to be biased about gender or race, or the model is learning that people over 100 are lower risk, the odds are a black box model trained on the same data would learn the same things, and you need to fix it there as well.
That is really helpful. So you're saying that you would have a black box model and then you would have an interpreter model. You train both of them on the same data, and then you would use the results from the interpreter model to try to diagnose. the black box model?
We often do that. You can also train, you can do distillation. You can train a glass box model to mimic the black box model if you want. And then if it's an accurate mimic, then it is telling you exactly what's happening inside the black box model in an interpretable way. And that's kind of what SHAP does. SHAP is it's an attempt to learn an approximation of the black box model that can be represented as like additive graphs. So SHAP is trying to do this when it generates its explanations. But one thing that's important is if the accuracy of the glass box method is equal to, or in the pneumonia case, better than the accuracy of the black box method, well, you'd be crazy to intentionally use the black box method when the glass box method is just as accurate. And the beauty of the glass box method is it's not only completely interpretable, but it's editable. You know, it preserves privacy more. Like it has a number of very nice properties. So if you're getting the same accuracy, you really shouldn't be using black box methods unnecessarily. And that's why we said we think the future really could be large language models and transformers for everything that has to do with text and images and planning. And it could be some kind of glass box learning for everything that has to do with tabular data.
Very helpful. Thank you so much.
Sure. Thanks for the questions.
Awesome. And then in the essence of time, I think we'll take 2 more questions, and then the rest we can take in the Slack. So the first question actually I want to take is for Krzysztof, and I'll read this one out. And the question for Krzysztof is, so during trajectory estimation in OD discovery work, so how do you account for noise and outliers that might be in the data set?
Yeah, so in the, I assume by OD discovery work, you mean so not the work I've just presented, look at kind of the related work, but also comment on my work as well. So the noise is really a big problem in OD discovery in general. It's one of the main challenges because when you want to learn an ordinary differential equation, you don't really get the label, which is the derivative. And the way to get this label is to do derivative estimation. And derivative estimation in general is quite challenging, but it's becoming even more challenging when it is noisy. And there are actually ways to counteract it based on weak formulations of ODEs and PDEs. And very coincidentally, this is exactly the kind of work I did, and with Zhao as well, Michael Lab some time ago. So we have papers about discovering both ODEs and partial differential equations from data in the presence of noise that uses this variational or weak formulation of ODEs. When it comes to my work, this problem is not as pronounced because we don't do any derivative estimation. We do not estimate the trajectories. We kind of learn them in an end-to-end way. So the issue with high noise and outliers is basically the same as in learning any other like machine learning algorithm. So there is no this additional challenge than you would have in OD discovery methods like Cindy. But just to be clear, we also compared with methods like WigCindy, which should be more that should work better with problems with high noise, and still these methods do not perform that well because of the inherent limits of closed-form equations. It just seems that either you get short equations, but they don't fit very well, and wherever you move to more real-world data sets, having compact closed-form expressions is just very difficult, even if you have quite powerful methods.
Awesome. Thanks so much for that, Krzysztof. And I think we'll end with the last question, which is for Dr. Caruana. And the question was around multimodality with EBMs. And the question was, what would it take, or can these methods be adapted to learn from images?
They're not really well suited to learning from images. So the problem is that when you learn from pixels, you're effectively needing a very high order interaction where you learn simultaneously these complex functions from many typically adjacent pixels. And our model, generalized additive models, and then all the variants of them are not designed to learn these high order interactions between things. So it can do very basic things. It can do like template learning and stuff like that, but it can't touch what deep learning is now doing on images. So the best we've done is we do some work in physics where the domain has a lot of images in it. And there what we do is we tabularize the images. So we convert the images, usually using physics domain knowledge, into tabular features, and then we do the learning on the tabular features. So this is some work that we're doing now. We presented some of this work a year ago at a machine learning and science kind of thing. And now some new work might be starting up with Sandia Labs. But it's not really a learning method designed to work on images, pixels itself. It would have to be some tabular version. And by the way, when they did the papers on Lyme and then later the papers on Schaap for interpreting black box models, they used images as their examples. But if you look carefully, what they really did was they tabularized the image into things like foreground, background, and stuff like that. And then they did Schaap explanations on the tabularized version of the images. They did not run Schaap on the pixels itself because Schaap can't. Just like our model, Schaap can't handle pixels. It's not an accurate function of pixels. So, and that's why I guess I started with that, history of machine learning and that dichotomy of where deep learning is going and where glass box learning on tabular data is going. And they're definitely, they were pretty much what was good for one was good for the other, let's say 25, 30 years ago, but that's no longer true. They have bifurcated into two very different worlds right now.
Awesome. Thank you so much for that, Rich. And thank you so much, everybody, for taking the time to attend today's session. And thanks so much, Rich, for joining. If
Sure,
you've
thanks for
if you've
inviting me.
enjoyed all of the work that Rich has presented and Krzysztof has presented, we look forward to seeing you also at the summer school in the coming summer, where we hope that both will be speaking at and you can learn much more on this topic area. And we look forward to seeing you next month, where we'll be talking about AI agents.
Thank you. Thanks, everyone.